We're in a particularly messy state. The thing is, it's a workshop, and the problem with workshops is they are for working. Well, what we've got in here are a load of messy engineers that would prefer to work than tidy up. So what I'll do as we're walking around, I'll try and explain to you what all the little bits and pieces are, which might help you with with your project, because it might sort of drop into place then. What this is called a backplate. And this goes on the front of the Spitfire, between the engine and in front of the propeller. So you've got a propeller that sits in here. These scallops here are where the roots of the propeller blade will stick out, and the engine will drive through the middle of this propeller. So effectively what that is the ring that runs around there. This is called a spinner, and this here is the back plate. And what you can see there, in a sort of slightly blurred way, is the propeller. And we've got a propeller similar to that just round the corner, which I'll show you in a minute. So that's a back plate, and so this would be a spinner here. So that's a spinner. This is an old one. This is a wartime one. This dates back to the period of the Battle of Britain. So it's quite old, 1940, 1941. It's a little bit ropey. People have had a go at cleaning it just to see what sort of condition it's like under the paint. And what that's come into us for is the person that owns it, knows the aeroplane that goes with it, has sent it to us and said, can you refurbish this for us? And a lot of what's on there probably will fly again. So it's sort of down to us to make a decision what's good and what isn't. So that's what that is. The other bit I can show you, we've got this here. Now this is a bit of a modelling exercise. This is a plastic model of what's called an exterior bulletproof windscreen. That's this bit here. So that's the screen that holds a big thick piece of glass. In there is glass, solid glass. Yeah, but it's a special type of glass. It's bulletproof glass. I don't know if any of you know what comes out of these wee beasties here. What? Bullets. Yeah, there's a special type of bullets though, they're not just bullets.
Is it a cannon shot?
Yeah, it is cannon, yeah. So that's what these fire. Now the problem with machine guns is whilst you wouldn't want to be shot with one, because a bullet from this, you could probably stand all you up in a line and it'd probably go through about 4 of you before it stopped, the bullet. And if you shoot another aeroplane with it, it'll go straight through the aircraft skin and it'll go into what's inside. And what you'd be trying to do as a fighter pilot is disable the other aeroplane. So you're not really just interested in putting holes in the aeroplane, you need to disable the aeroplane. So you want to try and hit the fuel tank, hit the engine, hit the pilot. You want to do something which will stop the aeroplane. What a lot of the pilots were complaining about during the Battle of Britain is they'd have an aeroplane in the sight, so you're a fighter pilot and you come down on the enemy and you fire your guns and you empty all your guns and you fill this aeroplane full of bullets, so it looks like a colander, and it still carries on flying because you haven't actually hit anything that's vital. So because of that, they thought, well, we need more stopping power, so we'll put cannons on, and that's what these are. So that's the tip of the cannon there, and the business end of the cannon, if you like, is back here. And a cannon shell stands about that tall, and the bullet part of it is probably about that tall, and it's 20 millimetres in diameter. You'll know what 20 millimetres are, don't you? Yeah. So that's probably a bit thicker than my thumb. Yeah, and it's about that long. But it isn't just a bullet because it's full of explosives. So when it hits what you're shooting, it explodes. So just as the cannon, the machine guns will go through the aeroplane, the cannon will go into the aeroplane and explode like a bomb. So that'll do a lot more damage. Now, what this is a bulletproof screen, and that's it there. And I've seen photographs. So you've got glass in there. I've seen photographs of a cannon shell. So I've told you how dangerous a cannon shell is. I've seen pictures of a cannon shell that's hit one of these things. Bear in mind, you're the pilot and you've got your head here, and you can see this cannon shell coming towards you between your eyes, if you like. And the bulletproof glass is so good that it stopped the cannon shell. So the cannon shell is stuck in it, sticking out like a carrot of this bulletproof glass. So that's how effective bulletproof glass is. Now, the problem that people such as I've got today is that if you're restoring an aeroplane and you need all these bits and pieces to make the aeroplane complete, and you want the aeroplane to be authentic, so what we have to do is try and recreate all these original parts. But the problem is we haven't got original parts. So I've made that model. That is a model. That's in resin, and that's copied from an original one. The original ones were an aluminium casting. This is a model, and just as you've made your plastic model, we need to make plastic models from which we then make the real things. So that's our plastic model. That's only half of it because there's another side. Now what this is the next stage on from that. This here is this is the first stage of what's called a casting pattern. Do any of you know what casting is? Yeah.
Is it when you get a molten metal and put it inside?
That's it.
A cast.
That's right. That's spot on.
It goes into shape.
That's it. So what you would do is you would I'll tell you what casting is, and it's very, very simple form. Just say I've got a bowl of molten metal here, and it's running like water. Tip it out, and it'll splash all over the floor and burn us all. But it's just liquid. Yeah. If you make a shape, and the very earliest castings, if you study things like archaeology, and when people were first experimenting with making castings, they basically get a piece of sort of dirt, earth, and they make a bit of a hole, and you make it into the rough shape of whatever you wanted. Say you're making a little model dog. So you poke around in this hole, and you make something that you think looks a bit dog-like on the inside. And you get your molten metal, you've melted it over your campfire, and it's all liquid, and you pour it in, and when the metal goes cold, you get all the earth away from around it, and what you've got is your model, and you think, well, that's a bit rubbish. I can try better next time. Well, that's your model, yeah? Well, nowadays, you can go to all sorts of fancy lengths to make what you're creating absolutely super duper. And so, what we're going to do here, instead of using a piece of dirt, this is going to be our casting pattern is going to be coated with ceramic, and it's going to be very, very fine, very, very detailed, and when the molten aluminium goes in, it will be exactly as the model that we've made, but it will be subtly different. Do you know why it will be subtly different? Yep.
Because it was made in the same way that we did it originally.
More subtle than that. What happens when you heat something up?
Change states.
It expands.
It expands. So what you do is you heat your molten metal up and it gets bigger. Yeah? You all know that, don't you? When you heat things up, it gets bigger. Yeah? So your molten metal goes into the mould big, and then as it gets cool, it shrinks. And it will be exactly the same shape, but it'll be a little bit smaller. And it'll be round about 1.6% smaller. So what we've got here, that's our model, and that's our finished size. And what we've got here is the next stage, which is the same thing, but 1.6% bigger. Can you all see that? Can you all see the size difference there? Can you see that? Yeah. And that's because when we use this now to create our model, when it shrinks, it will be that little bit smaller. Yeah. So that's what that is. And if you've got to be careful with this. If you just feel the weight of that, yeah, you can pass that round. I'm not too worried about that. So that's plastic. That's a resin. Yeah. Don't, whatever you do, drop that. That's very valuable.
What metals it takes?
I'll tell you in a minute. You feel how heavy it is. It's made of something called bismuth, which isn't really a proper metal. If I was to put that in the sink and pour boiling water over it, it'd melt. Because just as our aluminium would have to be heated over a campfire and got really hot before we could pour it, this stuff pours at about 70 degrees C. So that's a nice hot cup of tea, isn't it?
What is it again?
Bismuth.
What's that made from?
Bismuth is an element.
Alright, yeah.
It's classed as a semi-metal. It's got all the properties of metal, but it isn't actually a true metal. But it's very, very useful for pattern making because it's easy to work and easy to melt. And the life of this, it'll be quite short. As nice as that is, and there's gone hours and hours and hours into that, and when this gets made into a ceramic mould and when it gets made into a proper casting pattern, then that'll be finished with them. We don't need that anymore because we'll have that's the shape that we're after. The mould that'll be around that is what we want, and the mould will keep forever, but this bit we won't want again, and that will get melted down and made into something else. So it's got quite a short life. The only reason it's black is because we've painted it, just to give it a nice surface finish. So that's what that is, that's what that'll form. So the problem you have as engineers, you have to come up with all sorts of creative solutions as to how you're going to make things like that. Yes?
Would you repaint that? Or should
This, yeah, it will all be repainted, yeah. That's a cockpit door. It's not actually complete because there's some bits and pieces missing. And between me and you, it isn't a very nice cockpit door. This is one someone else has had a go at rebuilding, and they haven't made a very good job of it, and it's come to us to do right. But well, that's the door. So as you're sitting in, the cockpit door's on the other side of the aeroplane. As you're sitting in, this would be about where your shoulder is, so you're sort of looking out over the top. And the bit that's missing here is there goes a catch here, so you'd pull the lever that way and the door would open. Yeah. It came to us with another cockpit door that we had to rebuild. The pilots like to think they're very clever, but they aren't really. Engineers are a lot cleverer. The pilot took off with the door open, and the wind blew it open, and it pulled it all off the bottom. So when they break them, we fix them. So that's what that is. We're not getting very far in our tour, are we?
We need to look at the
I know,
which is what they're familiar with.
I know.
And the jig here.
See, I'm in trouble already. Right, we'll go look at something else. So that's the top of the skin. There's a seat here, and then there's a skin of aluminium which loops all around the top of the fuselage, and then here is an instrument panel. So your pilot seat's there, your feet would be about here somewhere, yeah, and the control stick that you steer the aeroplane with is here, yeah. So you'd sit with your feet down there and you'd have the control stick here. First proper fuselage frame. This one's called frame 5. It's a long and complicated story while that's called frame 5, which I'd love to tell you, but I'll get in more trouble, so I won't. So that's frame 5, and then behind frame 5.
So we're on here.
Right,
We're opposite way around actually.
Right, so that's
five.
frame 5.
Yeah.
Yeah. And then the area between frame 5 and where the windscreen starts. The windscreen's about here, so that our bulletproof casting would sit about here. Yeah. And the instrument panel. All that front cavity, if you can imagine, there's a big skin over the top of this. Yeah. The same sort of height as our door. All that space there is full of petrol. Yeah? So you're sitting with 90 gallons. Now what's that in litres? What's 90 gallons in litres? You won't know what gallons are. It's a lot.
200.
200.
Just over.
Yeah? So we've got all this full of fuel. Yeah? So you're a fighter pilot. And we know fighter pilots aren't very bright, don't we? Because you're going to take your aeroplane and you're going to fly over the enemy and they're all going to shoot at you. Well, that isn't very clever, is it? Well, that's what you're going to do. And they're going to be trying to set your fuel tank on fire when they're not trying to kill you. So it's a fairly dangerous thing to do. But you've got all this fuel there. Now, the Spitfire was designed to be what's called a dogfight aeroplane. It was designed so that when the Germans came over England during the last war, we'd send Spitfires up and we'd shoot them down. That was what happened during the Battle of Britain, which we did very well, and we sent them all back over the Channel and they went back to France. But then, as the war progressed, we needed to chase them through France and chase them all the way back to Germany. So the Spitfire had to get longer legs, it had to have more fuel, it had to go farther. Yeah? Yeah.
Wasn't there a problem at first with Spitfire, like when it went to do the measurement, it had to do a dive?
I'll tell you about that
all the
in a
fuel
minute
had
if
to
you
go
like. Yeah.
forward and it had to go down.
Yeah.
And then somewhat, I can't remember the name, but she made like a triangular cone
Yeah.
so that...
I'll tell you about that in a minute. Yeah. So you needed more fuel. So later Spitfires got fuel tanks in the wings, and they also got a fuel tank back here. So they got another 80 gallons behind the pilot. So now you're a pilot sitting between two enormous fuel tanks. Made it even more dangerous. And either side of you is more fuel. And they weren't content with that, and they ended up making what's called a drop tanker, which is another fuel tank that went under the belly of the aeroplane. That you, once you emptied that tank, you just pulled the cord, and it fell from the aeroplane, and you dropped it. That's like carrying a jerry can in your car and throwing it over the ditch when you're finished with it. So that's the sort of situation you find yourself in. You've got lots of dangerous stuff all around you. So what we're trying to do is with the simulator, we're trying to give people the opportunity to climb in. We're going to make it all out of authentic parts. It's all going to be as a proper Spitfire, and you'll be able to fly the Spitfire just as you would be able to fly a real one. What we were trying to do was make it have all the right material, so it felt right, it looked right, and it was as near as you could possibly be to being allowed to go and fly a Spitfire. So far as your question about the dive, if you think about, I don't know if any of you have seen films or programmes of Spitfires flying, but if you're flying a Spitfire straight and level and you want to go down there, either because you're chasing a German or there's a German chasing you, you can't just do that, because doing that causes fuel starvation in the carburettor. You know what a carburettor is? Carburettor is the bit that mixes fuel with air and squirts it into the engine, which creates an explosion which pulls the aeroplane along. Exactly the same as your car, but most modern cars have got something called fuel injection. But it's the same principle. You're mixing air with petrol. Petrol's very, very volatile. It burns and explodes very, very easily. It's actually more volatile than gunpowder, petrol is. You all take it for granted when you're filling up at the fuel station, but it's actually quite dangerous stuff. And you mix it with air, the right volume, put it into the engine, and that gives you power. But the Spitfire had a carburettor that caused fuel starvation. So when you do that, basically all the fuel went to the top of the carburettor, and the carburettor then has got no fuel to mix with its air. So the engine's just drawing in air, and it coughs and splutters and conks out. And that's just what you need under the German chasing you. So what they managed to work out was they put the aeroplane into a negative G situation, or took it out of a negative G situation and put it into a normal G situation. You're flying straight and level, you've got gravity pulling down on you, and that's pulling the fuel in the right place for the carburettor. When you do that, you beat gravity, you're accelerating towards the earth faster than the force of gravity. So everything that's inside becomes weightless. You've seen astronauts in space floating around. But then have you seen that aeroplane that flies in America where you can all bounce around the inside of it weightless? The fuel in the carburettor does the same thing. So there's always an engineering solution, and there was a very clever engineering solution to stop the fuel from leaving the chamber in the carburettor and staying where everybody wanted it to be. So
You can Google it actually.
yeah.
You can find out how to solve fuel starvation. The ideal mixture for an engine is 15 parts of air to 1 of petrol. And if that gets disturbed, then you get these problems that Mr. Harris was explaining. But you might want to say what the jig does.
Right, the jig.
To hold everything in place.
Yeah.
This great frame is called a jig, this great frame. And this holds all these components in the right place so that when you build the fuselage, it's not distorted.
It's not very easy for you to visualise at the moment because we've got it fairly well stripped down. If you'd have come about 2 years ago, we'd got a complete Spitfire in the jig, which would have looked like a full-size version of your model, but it was all in the jig. The purpose of a jig is if you've built your model, so you've got all your frames, you've made all your frames, they're very nice. You've made all your long run pieces, which are the bars that will be running the full length of the fuselage, and you've got them all in your hand and they're all loose, and you've got to stick them together. Now, what would you do, or how did you solve the problem of making sure that everything's in the right place?
Stuck them on and then stuck bits to it.
What did you stick them to?
Cardboard.
Cardboard. And what was the cardboard in any way marked out? Was it just a random piece of cardboard that you found lying around?
Put like the plans.
The model, it's occupying your man's time.
We need the model. We need the model now. This is important. Oh, yeah, this is it. We don't need the model now. That's not important. Right. So you've made all these, and you made a lovely job of making them. What are these lines for here? These lines here? They aren't wings. These here. What are them? These are the positions of the frames, yeah? So you've known that these positions are where the frames need to go, yeah? Now, if that's frame 13, and that's the position of frame 13, frame 13 is different than frame 12, isn't it? And it's different than frame 14. So if everything's correct on the drawings which have made this model, if you stick 13 in that position, and you do the same with 14, 15, all the rest of them, when you've finished, you'll have the right shape for your aeroplane, won't you? That's if you had the right information in the first place. Your Spitfire will almost take its own shape without you having to do too much. Now, what I've got here in this jig is essentially the same thing, but this is in 3 dimensions. This is just 2 dimensions, isn't it? Yeah. So this, what we've got is the same thing but in 3 dimensions. We'll put him there, I think. Put him there, I think he's reasonably safe like that. Now, as I say, the jig is fairly stripped down at the moment, but what we did, before we could build the fuselage, we had to make a very sturdy box frame, which is what this is. Yeah. So it's all made of steel, and it's all bolted together, and all the joints are machined so that everything is very, very accurate. And then onto that we've bought extra brackets that we've then made, like this one. Now these are bolted down, and they've also got something called dowels in, which are steel pegs essentially. And what it means is if I take that off and then put it back on again, it will go back on in exactly the same position, because that's critical. Because if every time we built a fuselage the jig moved about, they wouldn't be very good fuselages, would they? So everything has to be dowelled and accurate. So that's that. And then this bracket is picking up on this bracket. Now this bracket is part of the aeroplane. On the aeroplane, that bracket there is the rear wing spar attachment bracket. So where I'm standing now is on the back of the wing, or would be if we got a wing. And this bracket will run right the way out to the tip of the wing. And the pin isn't actually in at the moment. A naughty boy's lost it. But he's not listening at the moment, but he is in the workshop somewhere. But when that peg goes in there, that will put this frame, this one's frame 10, it will put that frame in the right position relative to the rest of the jig. Yeah. So that means it will be the right distance this way, and it will be the right distance from the centre of the plane, the axis of the plane, the middle of the plane. Yeah. Now, and as an engineer, what you've got to do, you've got to be able to very, very accurately get that in the right place, which involves lots of maths. Yeah? Do you all love maths? No?
It's okay.
Engineers have to like maths.
They're all good at it. You may not like it, but they all do.
Yeah. In order to make any accurate structure, you need maths. You know, one thing I will tell you though about maths, when you're sitting in a maths lesson, and maths lessons are boring, aren't they? They are boring. I used to be a teacher. I was a rubbish teacher, but I was a teacher. But you're sitting in a maths lesson, and the teacher's telling you all about maths and lots of other things. But it's difficult very often for you to be able to relate to the subject that you're being taught, and that's the trick really. That's the disadvantage of having a good education when you're young. You don't always realise what all the bits of information you're being given are for. It's like being taught to read. When someone first taught you to read, it was a fairly sort of dull, uninteresting thing, because you were just reading these very simple books. But without that gift, without being able to read, all the wonders of literature would be closed to you. So you've got to take in the knowledge when you're young to be able to apply it when you're older. And maths within engineering is a bit like that. When you're just being taught something in a maths class, your maths teacher hasn't got time to explain all the wonderful things you could do with that maths if you chose to become an engineer. You just have to learn and pass the tests. But there is lots and lots of maths in engineering. And you've got to be able to calculate the positions of everything on this jig. So we've got this position here, which is frame 10. At the front, we've got frame 5. And frame 5 is the main wing spar attachment for the Spitfire. So now, this will be a difficult one for you to be able to perhaps visualise, but if you look over on the wall there, can you see that big brown board? Well, at the bottom, you've got a little piece of a wing spar. Now, that wing spar is actually out of a Mark II Spitfire that was in the Battle of Britain. And that, if you look at the 3 holes, can you see the 3 holes there at this end? They are the same 3 holes that are here on our frame 5. Now, unfortunately, what we've got at the front of that frame 5 is an old, corroded, original part. Yeah? But you can just about see that there were once 3 holes there. You can see there are 3 holes on the front piece still. And that's where that wing spar would bot. Now that wing spar runs the whole length of that brown board that's on the wall. And all those little angle-shaped positions all across it are the coordinates of the wing spar must follow, because you've all struggled making this because there's no straight lines, are there? Everything's curved. Everything on a Spitfire is curved, and the wings are no different. The wings are an elliptical shape. It's not just because they look pretty, but just as the fuselage is covered in curves, the wings the same. So that's the forward wing spar. This is the rear wing spar. The distance between the two is absolutely critical on our jig, because if you suddenly happened upon a load of money and you decide, well, I'd like a Spitfire, and we say, well, we'll make you a fuselage, and you get somebody else to make your wing, they could make you a wing anywhere else in the world, wouldn't matter where it was made. But if you get your wing and you've got our fuselage and you come to put the two together, it's fairly important that they fit together, which is why engineering drawings and the maths that support the engineering drawings are so critical, because you've got to have parts that fit together. Otherwise we're all wasting the time. So that's the purpose of an engineering drawing, and for us to do the drawing justice, we've got to make jigs which are as accurate as the drawing tells us that they are. So as an engineer, as you start to create something like a jig, you need to make sure that you've put everything in the right place.
I think we need to have a look at the
Yeah, we'll go. That is
the
a fuel tank, indeed it is a fuel tank. That's a lower fuel tank, and it sits down here. A quick story about a fuel tank. The fuel tanks used in Spitfires during the war were quite clever. You shoot a bullet through that full of petrol. It's got to be full of petrol for this to work. So you've got it full of petrol and you shoot a bullet straight through, and the bullet goes in one end and it comes out the other. You would expect it to start piddling fuel out all over the place, wouldn't you? But it won't. Because what they've done is they've coated the fuel tank in a very special chemical solution that reacts with fuel. And as soon as petrol goes onto this substance, it fizzes up. It's a bit like that gap filling foam that people stick windows in with today. And it seals the hole up, so it plugs the hole. So you can fill the tank full of holes and it won't leak. You'll get a few little dribbles out, but it won't spill its contents all over your feet and set you on fire. In theory. Now this is called the centre cone. This is part of the spinner. Remember I showed you the spinner at the front. So we've got the nose cone. Jake, bring me the nose cone now. You'd make a rubbish magician's assistant, you would. No. So that's our centre cone, and that is going to fit over there like that. So you can see now roughly what it's going to become. Now we've made that bit. You can hold it. Put it on your head, do what you want with it.
How do you think that's been made? How do you think it's been made?
It's been a fully cone shape.
I'll give you a clue. It won't really help you in any way, but it's a clue. Have any of you got saucepans at home?
Oh, yeah,
Pots, pans, woks?
And then they put it on the saucepan.
Yeah, made exactly the same way.
It's done at high speed. Very dangerous process.
Have you seen the potter's wheel? Where you play and you same with metal. Bit more sophisticated, but the same basic principle. Starts off as a flat sheet, and you basically force it, spin it, and force it over a shape. In this case, it's the front cone of a Spitfire. Yeah. Anybody else want to put it on their head? Wear it? When you have a look at it, if you take it back to Jake, you'll put it somewhere safe. Can you take it back to Jake there? Mind you don't trip over anything. That's the same. If you look at that, there's a little bit of a clue there as to what shape it once was. See this writing? There. Yeah. That writing was printed onto the sheet when it was flat. So effectively, what we've got there's another. This is steel, but see how it's got this writing on. All the materials you have to use for the aircraft industry have got to be. They've got to be. They're very special materials. They're very closely controlled. The material composition is, and they also have to be what's called traceable. So if I was to need to know all about that piece of material, and you see it's got a BN number there. When this was on a big sheet and it came into us, we had to write this number on it, and it's all entered onto the computer, and that'll end up making an aeroplane part, and it can go off to the far side of the world, and in 50 years' time, that might be in an incident, might be an air crash. Might not be anybody's fault, but it's in an air crash. And if the air crash investigators want to know something about the material that we used when we made it, on the job cards which control what we've made will be that batch number. And I can then say, yeah, well, that was made on such and such a day by Jake. He's always getting me in trouble. And it was made to whatever drawer it was made to, and I know it was this one.